Okay, so in this video we will be doing the topic distributions associated with Poisson process. Okay, so in these distributions there are a few main distributions that we will discuss over here. Okay, so the distributions are mainly exponential distribution. Okay, it is one of the main associated distribution with the Poisson process. The second one is the gamma distribution. Okay, and the third one is the normal distribution. Okay, so these three are the main distributions that are associated with the Poisson process. Okay, so first of all I will briefly explain the Poisson process, its own distribution, and then we will go towards the exponential distribution. Okay, so the Poisson process, what does it do? It is actually related to counting process. Okay, counting process. What does it count actually? It counts the number of events occurring over time period t. Okay, so from 0 minutes to t minutes, the number of events occurring n of t, this is predicted by the Poisson process. Okay, and we know that the probability of number of events over time t is equal to k. It is equal to lambda t raised to the power k e raised to the power minus lambda t divided by k factorial. Okay, so this is one of the main thing in the Poisson process. Okay, now we will move towards the exponential distributions, and we will explain, like we will let know that how exponential distribution is associated and what does it do in the Poisson process. Okay, so let me write it over here. Exponential distribution. So the main graph that is associated with the exponential distribution is, there are two kinds of exponential distributions. Okay, one is the negative exponential distribution and one is the positive exponential. Okay, this is the negative, this one is positive exponential distribution. Okay, this one is e raised to power minus lambda t, and this is equal to e raised to power lambda t. Okay, it means that initially this parameter is high, but as the process goes on, the parameter decreases. Okay, while in the positive one, initially the parameter is quite low, but as the time passes, the parameter becomes high and high. Okay, for example, the radioactive material we talk about the radiations. Okay, so initially the radiations are very high. Okay, this is a substance, okay, a radioactive material actually. Okay, so the radiations emitted initially, okay, these are very high, and then the process slow down. Okay, the process is slow down, okay, until the material is decayed completely. So this one follows the negative exponential distribution. Okay, and when we reverse the process, vice versa, do the vice versa, it is the positive exponential distribution. Okay, I hope you have got the idea that of the exponential distribution. Okay, but now I will explain it in terms of the association with the Python process. Okay, so the exponential distribution is quite, related to the Python process. How it is related? It is related with inter-arrival times. Inter-arrival times. Okay, like for example, this is the graph of a Python process that is happening. Okay, this y represents x of t or n of t, you can say any. Okay, this is the number of events occurring. Okay, number of events occurring. Okay, and this x represents the time frame, okay, the time period. So initially, okay, initially there is no event occurring. Okay, initially there are 0 events occurring. Okay, so after some time, for example this time, okay, this is t1, okay, an event starts to occur. For example, we are in a shopping mall. Okay, you are the owner of a shopping mall, you are observing the arrival of the customer. Okay, so you open at 8 a.m. Okay, this is 8 a.m. you have no customers arrive at that time. Okay, now after 5 minutes, for example, the t1, this is the the time gap. Okay, you have one customer that has arrived. Okay, so the first event have occurred. So after some time, there is a second event that has occurred. After there some time, the third event occurring. Okay, and fourth one, and fifth one, and so on. Okay, so you see that there are number of events occurring at random times starting from 0. Okay, so the waiting time for the nil customer, no customer, it is 0. Okay, w represents the waiting time. Okay, so now here the first event is occurring at this point. Okay, so this is w1. W1 is the waiting time until first event occurs. Okay, similarly w2 is the waiting time until second event occurs, and so on up to wn, which is the waiting time until the nth event or nth customers appear. Okay, in this video we will be discussing the gamma distribution and how it is related to or associated to Poisson process. Okay, so in a Poisson process, okay, which has a rate of lambda is the rate of the process, okay, per unit time. For example, customers arriving in a shopping mall, or number of calls received per hour in a workstation, something like that. Okay, so lambda is the rate of the process for the Poisson process. Okay, so how does the gamma distribution work? The gamma distribution actually, it shows the time until the kth event occurs. Okay, it represents the time until the kth event occurs. We know that there are a number of events occurring over the time period, okay, like the first event occurring, and then the second event, and then the third event, and fourth event, and so on. Okay, so over the time when these events occur, okay, so for the first event to occur, it follows the exponential distribution. I will let you know like why it follows only exponential distribution and not gamma distribution. Okay, but all the other events actually, okay, up to the kth event, they follow the gamma distribution. Okay, and it can be represented as, okay, so the waiting time actually Wn or k has gamma distribution. Okay, and this is the time until the nth event has occurred. Okay, we can also represent it as wk for kth event. Okay, so the probability density function PDF, which is represented by small f w n over the time period t, it is equal to lambda raised to the power n t raised to the power n minus 1 e raised to the power minus lambda t divided by n minus 1 factorial. Okay, so if we put the value of n is equal to 1, like for the first event only, as we said that the first event, the waiting time, it follows the exponential distribution. So we get fw1 of t is equal to lambda t raised to the power 1 minus 1 e raised to the power minus t divided by 1 minus 1 factorial. So it will be equal to lambda e raised to the power minus t. Okay, and this is exponential distribution, and in particular it is negative exponential distribution. Okay, so only for the first waiting time for the first event it is following exponential distribution, but for the rest of it up to nth it is following the gamma distribution. Okay, to prove this, that the PDF small f Wn of t is equal to lambda raised to power n t raised to power n minus 1 e raised to power minus lambda t divided by n minus 1 factorial. To prove it, what we need to do is we need to find the cumulative distribution function, okay, the CDF, which is the capital Wn of t, okay. So what is this equivalent to? This is equivalent to the probability that there are the waiting time is less than or equal to the total time t, or there are more than n events in this time period. Okay, the number of events in time period t are greater than or equal to n, or the waiting time, okay, the waiting time is less than or equal to the time period, and the waiting time up to the nth waiting time for the nth interval, nth event to occur. Okay, so if we see this or this follows the Poisson distribution, just like we do in Poisson, that probability of x of t is equal to a k, it is equal to e raised to the power minus lambda t raised to the power k divided by k factorial, okay. It follows Poisson distribution. So as there are n events, okay, so the summation of these events follows this gamma distribution, okay. So it can be written as the probability that there are the waiting time for the nth event is less than or equal to the time period t, it is equal to summation of k is equal to n up to infinity, okay. It means that the nth event has occurred, okay, and we have n or more than n events in this time period t, okay. So it is equal to summation of lambda t raised to the power k e raised to the power minus lambda t divided by k factorial, okay. Okay, remember the case that we used about the P and Q, okay. This is the probability for an event, okay, and Q is the probability for the all other events, okay. For example, we have 5 events, okay, we have 5 events. So we say that the probability of event 1 to occur is 0.5, okay. Then the probability of all other 4, okay, 2, 3, 4 and 5 events is equal to 1 minus this, it is equal to 0.5, okay. So we will use the same rule over here. We have the probability that the total number of events are greater than or equal to n. Okay, and it is equal to summation of k is equal to n up to infinity, because we are sure that we have n events, okay, or more than n events. So we will make the summation from n to infinity. Okay, summation of lambda t raised to the power k e raised to the power minus lambda t divided by k factorial. Now it can be interchangeably, just like I explained in the PQ, it can be written as 1 minus summation of, here we used k is equal to n, so in this it will be from 0 to n. So k is equal to 0 up to n. Sorry, n minus 1, because it is starting from n. So all the events before n, summation, make the summation and subtracting it from 1, it will give us exact probability for this one. Okay, so we can write it as lambda t raised to the power k e raised to the power minus lambda t divided by k factorial. Okay, and we know that the PDF, okay, it is equal to the differential of the CDF. Okay, and this is equal to the CDF. This is the CDF. Okay, so when we make the differentiation of this, we get d by dt of capital F W n of t is equal to d by dt of 1 minus summation of k is equal to 0 up to n minus 1 lambda t raised to power k e raised to power minus lambda t divided by k factorial. Okay, when we make the differential, okay, we get the exact same equation as we found before, which is small f waiting time t, and it is equal to lambda raised to power n t raised to power n minus 1 divided by n minus 1 whole factorial into e raised to power minus lambda t. Okay, I didn't do this differential actually, but you can do it. It is not very difficult. When you differentiate it, the thing that you need is this thing. Okay, this is the probability density function PDF for this case. Okay, so the probability that the time for the nth event to occur is less than or equal to t, okay, is equal to 1 minus summation of k is equal to 0 up to n minus 1 lambda t raised to the power k e raised to the power minus lambda t divided by k factorial. So this is the equation that we will be using. Okay, and it is also the CDF. cumulative distribution function, okay, which is represented by the capital F waiting time of nth event in the time period t. Okay, now I will do an example of it, okay, so that we can actually see how this gamma distribution works. Okay, so the example says that a website receives 5 visits per hour. Okay, we have a website, okay, and the rate of visits is 5 visits per hour. There are 5 clicks per hour on that website. It says that what is the probability that third visit occurs within 30 minutes. Okay, so just look at this thing. Okay, this is Tn. Now this n here, we want to find the probability that the third visit, which is T3, okay, it occurs within 30 minutes. Within 30 minutes means that within half hour. So it must be less than or equal to 0.5, because 30 minutes is half hour. Half hour is equal to 0.5 or 1/2 hour. Okay, so it will be equal to 1 minus summation of k is equal to 0 up to n minus 1 lambda t raised to power k e raised to power minus lambda t divided by k factorial. Okay, so we put the values over here. Okay, t is equal to 0.5 over here. Okay, and we have n minus 1, so n is equal to this 3. Okay, so what we have is the probability that the third visit T3 is less than or equal to 0.5 is equal to 1 minus summation of k is equal to 0 up to 2 n minus 1. So n minus 1 is equal to 3 minus 1 is equal to 2. So I wrote 2 over here. Okay, lambda is 5 visits per hour. Okay, so I will write it as 5 into t is equal to 0.5. So 5 into 0.5 raised to the power k. Because k is variable over here, it is starting from 0 up to 2. So we will write k over here. Okay, we will not put any value over here. E raised to power minus lambda t, which is minus 5 into 0.5 divided by k factorial. Okay, so it is equal to 1 minus, now put k is equal to 0, k is equal to 1 and k is equal to 2 in this. So first putting k is equal to 0. So we have 5 into 0.5 raised to the power 0 and e raised to power minus 5 multiplied by 0.5 divided by 0 factorial. Okay, plus 5 into 0.5 raised to the power 1. Okay, multiply by e raised to power minus 5 multiply by 0.5 divided by 1 factorial, plus now put k is equal to 2. So we have 5 into 0.5 raised to power 2 dot e raised to power minus 5 into 0.5 divided by 2 factorial. So add the results of this and this and subtract it from 1. So it will give us the probability. So it is equal to 1 minus 5 into 0.5 raised to power 0. Anything raised to power 0 is equal to 1 multiplied by e raised to power minus 5 into 0.5 is minus 2.5. And 0 factorial is also 1. So it will give us e raised to power minus 2.5. Here it will give us 2.5 e raised to power minus 2.5. Okay, plus it will give us 2.5 square, which is 6.25 e raised to power minus 2.5 divided by 2 factorial. So it will give us 2 into 1. Okay, now putting the value of e and we can also do it another way, like 1 minus keeping the e constant over here, so collecting e from it, e raised to power minus 2.5, we get it common, so we will get 1 plus 2.5 plus 6.25 divided by 2. So it will give us 1 minus this is 3.5, and it will give us 3.5 plus 3.12. Okay, so it will give us 1 minus e raised to power minus 2.5 into 6.62. Okay, so 1 minus, so this e raised to power minus 0.25, it gives us 0.0821 into 6.62. So it will give us 1 minus 0.5435. Okay, so it will give us 0.4564, which is 45.64% chances. Okay, so we have 45.64% chance that the third event is going to occur within half hour. Okay, so that is how we use this gamma distribution. Okay, so in this video we will be talking about the binomial distribution associated with Poisson process. Okay, one thing that we should remember is that we have two kinds of distributions that come into act when there is conditioning. Okay, whenever there is conditioning, okay, by conditioning I mean that we want to know the probability of an event. Okay, for example, probability of xn or xu is equal to k, such that probability or the number of events in the total time interval t are n. Okay, now this probability is conditioned on this one. Okay, we have total number of events xt is equal to small n. Okay, and based on this we need to find the probability that the number of events in time interval u is equal to k. Okay, so whenever there is conditioning, okay, we have two kind of associated distributions, okay? The first one is binomial. Binomial distribution, okay? And the second one is the normal distribution. Okay, for now, up till the lecture 2, we will do only the binomial, and inshallah in the lecture 3 or 4, we will also be doing the normal distribution. But for now, we are just discussing the binomial distribution, okay? Now, it has a theorem, okay, and it states that it's theorem 3.3, okay, and it states that let x of t is a Poisson process with the rate of lambda greater than 0, okay? Rate of a process is always greater than 0, okay? Then we analyze it, okay? So then for u between 0 and t, okay, t is the total interval, u is somewhat between 0 and t, okay? The total interval is 0 and t, okay? So for this interval actually, and the number of events which falls between 0 and n is the total number of events, and k falls somewhat between 0 and n, we have the probability of xu, okay, at this time interval is equal to k, such that the total number of events in time t interval is equal to small n. This is the n is the total number of events, okay? So how to find this? We need to find this using the binomial distribution, okay? And I will provide the proof and all, but writing the final form of it, probability of xn is equal to xu is equal to k, such that the total number of events in time interval t is equal to n, it is equal to n factorial divided by k factorial into n minus k whole factorial, okay, u by t raised to power k into 1 minus u by t raised to the power n minus k, okay? And this is what the binomial distribution is. This is the binomial distribution. This equation actually represents the binomial distribution with n and p, where n is the total number of events and p is the probability of each event, okay? So whenever there is conditioning based on the number of events, we can find the probability of certain events in a subset of time interval t. U is a subset of a time interval t, so we can find the probability in that interval, okay, using the binomial distribution, okay? Now let's prove it, okay? Okay, so whenever there is conditioning, okay, for example, we want to find the probability of xu is equal to k, such that we have the total number of events in time interval t is equal to n, it is equal to probability that x of u is equal to k and x of t is equal to n divided by the probability that x of t is equal to n, okay? Now to end this end, okay, we have, okay, we have to introduce the middle interval, okay? For example, this is probability of xu is equal to k such that xt is equal to n. It will be equal to, now 1 is this probability, okay, that is for sure. Okay, so we will write the probability of x of u is equal to k multiply by, it is n, so it will be multiplied by. Okay, now to multiply it, actually we multiply it with this next one to multiply it, because we have the total interval t and the subset of k, so it will be multiplied with n minus k. Okay, so probability of x of u x of t, actually x of t minus x of u, okay, is equal to, this is total and this is the subset, so it will be equal to n minus k. Okay, and the denominator will remain same, which is the probability of x of total interval is equal to n. Okay, so let's do it further. We get x of u is equal to k such that x of t is equal to n. It will be equal to probability that x of u is equal to k multiply by, we can write it as the probability of x of t minus u. We can also write it like this, is equal to n minus k divided by probability of x of t is equal to n. Okay, now using the Poisson distribution. Okay, what does the Poisson distribution tell us? The Poisson distribution tells us that the probability of x of t is equal to n is equal to, okay, it is equal to e raised to the power minus lambda t dot lambda t raised to the power n divided by n factorial. Remember this thing. Okay, so we will use the same formula for this one, and for this one. So putting the respective formulas here, t will be replaced by u and n will be replaced by k. So it will be equal to e raised to power minus lambda u into lambda u raised to power k divided by k factorial. Okay, similarly here it will be e raised to the power minus lambda into t minus u multiply by lambda into t minus u raised to power n minus k divided by n minus k factorial. Okay, so putting those values, okay, so the probability of x of u is equal to k such that x of t is equal to n, it is equal to, okay, the first one is that probability of xu is equal to k. Okay, so it will be equal to e raised to power minus lambda u dot lambda u raised to power k divided by k factorial. Okay, multiplied by the second one is probability of x t minus u is equal to n minus k. So it will be equal to e raised to power minus lambda into t minus u. Okay, so e raised to power minus lambda into t minus u dot t minus u lambda t minus u raised to power n minus k divided by n minus k whole factorial divided by probability of x of t is equal to n. So it will be equal to e raised to power minus lambda t dot lambda t raised to power n divided by n factorial. Okay, so here it will be equal to the denominator, actually it is multiplication, so a by b multiplied by c by d, it is equal to ac into bd. So the upper will be multiplied with upper and lower will be multiplied with lower. Okay, so we get the probability of x of u is equal to k such that x of t is equal to n is equal to e raised to power minus lambda u dot lambda u raised to power k multiplied by e raised to power minus lambda t plus lambda u. Okay, and lambda into t minus u raised to power n minus k divided by k factorial into n minus k whole factorial. Okay, divided by e raised to power minus lambda t dot lambda t raised to power n divided by n factorial. Okay, now the situation is like this. Okay, we have this equal to a divided by b, this is b, divided by c, this is c, divided by d, which is n factorial. So it will be equal to a divided by b multiplied by d by c. Okay, so we will get ad divided by bc. Okay, so this one, the upper one is a, d is this one. Okay, n factorial. So doing it this way, we get the probability of x of u is equal to k such that x of t is equal to n is equal to n factorial into e raised to power minus lambda u dot lambda u raised to power k dot e raised to power minus lambda t plus lambda u dot lambda into t minus u raised to power n minus k divided by k factorial into n minus k whole factorial multiplied by e raised to power minus lambda t dot lambda t raised to power n. Okay, so n factorial divided by k factorial into n minus k whole factorial, this will be separated. Okay, multiplied by. Okay, now seeing this has the base of e, this is also base of e. Okay, so let's make it common using the base. So we have minus lambda u minus lambda t plus lambda u. So lambda u and plus lambda u, it will be cancelled. Okay, and we will have lambda u raised to power k into lambda t minus u raised to power n minus k divided by e raised to power minus lambda t dot lambda t raised to power n. Okay, so we get n factorial divided by k factorial into n minus k whole factorial. Okay, e raised to power minus lambda t multiplied by lambda u raised to power k into lambda t minus u raised to power n minus k divided by e raised to power minus lambda t dot lambda t raised to power n. So this is e raised to power minus lambda t and this is e raised to power minus lambda t. They both will cancel each other. Okay, so we will get n factorial divided by k factorial into n minus k whole factorial dot lambda u raised to power k lambda t minus u raised to power n minus k divided by lambda t raised to power n. Okay, so it will be equal to lambda n factorial divided by k factorial into n minus k whole factorial. Okay, so it will be equal to lambda u raised to power k. Okay, let's separate these. Okay, so lambda t raised to power n minus k and minus lambda u raised to power n minus k divided by lambda t raised to power n. Okay, so it will be equal to n factorial divided by k factorial into n minus k whole factorial into lambda is common in all of these. Okay, so taking the lambda common. Okay, so u raised to power k t raised to power n minus k minus u raised to power n minus k divided by lambda into t raised to power n. Okay, so lambda will be cancelled with the lambda. Okay, I will continue this in the next video. Okay, so the equation will become probability that x of u is equal to k such that x is equal to n is equal to n factorial divided by k factorial into n minus k whole factorial u raised to power k so t raised to power n minus k minus u raised to power n minus k divided by t raised to power n. Okay, so the power of these two is same, so we can write it as t minus u raised to power n minus k, because the power is same, divided by t raised to power n. Okay, so n factorial divided by k factorial into n minus k whole factorial. Okay, this thing, okay, it will become u by t raised to power k into 1 minus u by t raised to power n minus k, which is the binomial distribution with n and p, where n is the number of events and p is the probability of each event. Okay, I will solve some example on this. Okay, so let's solve an example based on this. Okay, okay, the example says that the customers arrive at certain facility with rate of lambda is equal to 2. Okay, 2 customers. Okay, so this is 2 per hour. Customers are arriving at a facility at the rate of 2 customers per hour. Okay, and they say that x of t is equal to the number of customers that has arrived up to time t. Okay, so in this video we will be doing some exercise problems. Okay, so let's suppose the first problem that we do over here is exercise 3.1. okay, we have some data given, okay, which is the problem says that a radioactive source emits particles according to Poisson process of rate lambda is equal to 2 particles per minute. Okay, we have a radioactive material which emits radiations or particles with a rate lambda is equal to 2 particles per minute. Okay, and we know that this is a Poisson process. Okay, so it says that what is the probability that the first particle appears after 3 minutes. Okay, we have to find the probability, okay, that first particle, okay, T1 appears after 3 minutes. Okay, so the time for the first event to occur is greater than 3. Okay, we need to find this thing. Now how to find it? Okay, we know that recall that the first event in a Poisson process actually follows exponential distribution. And in particular it is negative exponential distribution, e raised to power minus lambda t. Okay, and the graph it will make is like this. Okay, for the initial event to occur, the waiting time is a bit higher, but for the next events to occur, the waiting time reduces gradually. Okay, or we can say that the waiting time reduces exponentially. There is a rapid change in the waiting times. Okay, and the rapid change is negative, it decreases. Okay, so we can use this equation actually, e raised to power minus lambda t, to solve this question. Okay, whenever there is, the question asks for the first event to occur, simply go for the exponential distribution. Okay, now we know that this is the Poisson process. Okay, this is x of t, number of events occurring over time t. This is the first event occurring, this is second, and this is third, and so on. Okay, so y represents the x of t, which is the number of events occurring over the time period t, and the time period is 0 and up to t. This is the time period frame. Okay, and the x-axis, okay, this represents the time period. Okay, so this is where the first event occurs at this point. Okay, so this is W1, and the difference between, as we know that W0 is equal to 0. Okay, so the sojourn time is equal to W1 minus W0. Okay, so we can solve it by using the probability that T1, or we can say that T1 is also the sojourn time S0. Okay, is greater than 3, and it will be equal to e raised to power minus lambda t. So e raised to power lambda we have is 2, and t over here is 3 minutes. Okay, because we have probability that ti is greater than small t is equal to e raised to power minus lambda t, where I is equal to 1. Okay, for the first one only. So we can say that the probability that T1 is greater than small t is equal to e raised to power minus lambda t. This is the exact equation that we will be using. Okay, so small t over here is 3 minutes. Okay, so we will put the values. So it becomes e raised to power minus 6, and it will give us a value of 0.002478, or we can say that 2.48% chances that the first particle is emitted after 3 minutes. Okay, if we have 2 particles emission per minute, okay, so there is only 2.5% or 2.48% chances that the first particle is emitted after 3 minutes. Okay, so this is the first problem that we solved using the exponential distribution. Okay, keep in mind, okay, there are some hints, okay, that I will write over here. Okay, hints. Whenever we talk, or the question talks about first event, okay, go for the exponential distribution. Okay, or when it talk about the inter-arrival time, okay, inter-arrival time is the time between two events. Okay, time between two events. This also follows the exponential distribution. Okay, so this is something that you need to keep in mind when there is a problem that needs to be solved using the exponential distribution, or okay, now we will move towards the second problem. Okay, in this video we will try to solve the problem 1, that is exercise 3.1, using another method. Okay, using the sojourn times. Okay, so we know that lambda is equal to 2 per minute, which is the rate of particle emission. Okay, this is given to us. Okay, and we need to find the probability. Okay, here is this is x of t, this is t. Okay, this is the time where the first event is occurring. Okay, and so on. So this is the W1 actually. Okay, so difference between W1 and W0, okay, it is equal to S0, which is the sojourn time. Sojourn time is the time when the system is in that particular state actually. Okay, and what is that particular state? The particular state is that the first emission is done over here. Okay, so probability that S0 is greater than 3, it means that the probability that the systems emits the first particle is greater than 3 minutes. If we need to find this, okay, we know that the PDF of the sojourn times is equal to f of sk, this is equal to lambda e raised to power minus lambda s. Okay, so the probability for S1 is equal to lambda e raised to power minus lambda S0, this thing. Okay, now to find the probability that S0 is greater than 3, it is equal to integral of lambda e raised to the power minus lambda t dot dt, and because we want to know that if it is greater than 3, so the lower limit will be 3 and the upper limit will be infinity. Okay, so now put the values over here. Okay, we see that the probability that sojourn time is greater than 3, it is equal to it will become integral of 3 up to infinity to e raised to power minus 2t dot dt. Okay, so it will be equal to integral of 2 will be equal to 0. Okay, because it is and it will be equal to e to the power minus 2t, and it will be equal to this thing. Okay, the limits. So putting the values, we get e raised to power minus 2 into 3. Okay, so e raised to power minus 6, which is exactly the same value, okay, that we achieved earlier. So we can also use this method to find the, for a particular event, if we want to find that the probability that the time is greater than some particular minutes or hours, or just like we have like 3 minutes over here, we can use this formula, okay, using the integral. So that is also an option. If you don't want to use the integral, just use the formula, but that is for only the first one, okay, e raised to power minus lambda t, but for only the first event, while this can be used for the second, third sojourn time, fourth sojourn time, and so on. Okay, now let's move to the second question. Okay, we have exercise 3.2. okay, it says that a radioactive source emits particle according to Poisson process of rate lambda is equal to 2, which is the same as 3.1. okay, the that statement is same. So there are two parts, okay, for this. The first part is, what is the probability that the first particle, okay, the first particle or the first event actually appears sometime after 3 minutes but before 5 minutes, okay. The probability for the sojourn time S naught is between 3 to 5 minutes. So 3, we need to find this. And the second one is the probability that exactly one particle is emitted, okay, exactly one particle, n, one particle is emitted in interval from 3 to 5 minutes, okay, which is the probability that x of t is equal to 1 is to be found where t is equal to 5 minus 3, okay, between 5 and 3. So the exact time is 2 minutes, 5 minus 3 minutes, okay. We need to find these two, okay. So let's find the first one. The probability that the sojourn time is between S naught, the first sojourn time, is between 3 and 5 minutes, needs to find. So this can be written as the probability, okay, that S naught is greater than 3, okay, minus the probability that S naught is greater than 5. Okay, why we subtract it? We subtract it because the sojourn time we need to find is below 5, okay, and greater than 3. So we subtract it for the sojourn time greater than 5, okay. So it automatically adds the sojourn time for less than 5 minutes but greater than 3, okay. So that is why we subtracted it, okay. So using the same formula of e raised to power minus lambda t, okay, because it is the first first emission, okay, because we have S naught means the first emission, okay, or the first event to occur. So you will use this formula, okay. So for S naught greater than 3, we will have e raised to power minus 2 into 3. We put lambda is equal to 2 and t is equal to 3 because S naught is greater than 3 over here, minus e raised to power minus lambda will remain same 2 and t will be 5, okay. So e raised to power minus 6 minus e raised to power minus 10, okay. So it will be equal to the probability that sojourn time is between 3 and 5 minutes, and it will be equal to, this one we already know because we found it over here, e raised to power minus 6, which is 0.00248 minus e raised to power minus 10 will give us 0.000045. Okay, so make this, it will become 0.00243, which is equivalent to 0.24% chances that the first emission is between 3 and 5 minutes. Okay, I will do the part B in the next video. Okay, so for part B of question 3.2 exercise, okay, we need to find actually the probability that x of t is equal to 1, okay, where t is equal to 5 minus 3, okay, because we want to find that exactly one particle, this one particle is emitted between 3 and 5 minutes. Okay, so we use the Poisson distribution formula, which says that probability that x of t is equal to n, okay, it is equal to e raised to power minus e raised to power minus lambda t raised to power n divided by n factorial. Okay, so here we need to know that t is equal to 5 minus 3 is equal to 2. So the probability that x of 2 is equal to 1 is equal to, and we know that lambda is equal to 2 per minute. Okay, so e raised to power minus 2t and 2t raised to the power 1, because n is equal to 1 over here, and 1 divided by 1 factorial. So it will become e raised to power minus 2 into t over here is 2, so putting the values we get e raised to power minus 2 into 2 dot 2t, while putting the value of t is equal to 2 raised to power 1 divided by 1 factorial will become 1. Okay, so it becomes e raised to power minus 4 dot 4. So for e raised to power minus 4, it will give us a value of 4 multiplied by 0.0183. Okay, this is equal to e raised to power minus 4. Okay, so we get the value as 0.0732 or 7.32% chances, okay, that exactly one particle is emitted between 3 and 5 minutes. Okay, now move to the third problem. Okay, so exercise 3.3, okay, it says that customer enter a store according to Poisson process of rate lambda is equal to 6 per hour. Okay, by the way, these are the problems that I am doing. This is page number 294. Okay, so customer enter a store according to Poisson process of rate lambda is equal to 6 per hour. Okay, so lambda is equal to 6 per hour. Okay, this is the arrival rate. Suppose it is known that but a single customer entered during the first hour. Okay, during first hour it is known that customer entered is equal to 1. Okay, which okay, it says that what is the conditional probability? We need to find conditional probability. Okay, the conditional probability that this person, that first person that entered, okay, this person entered during first 15 minutes. Okay, here the rate is 6 per hour. Okay, this is hourly rate during first hour. This is also hour, but here we have 15 minutes. So 15 minutes of an hour, it becomes 1/4. Okay, or we can say that 0.25 hour. Okay, so what we need to find is, we need to find the probability that x of 0.25, okay, in the 15 minutes is equal to 1, such that we have x of t, which is 1 hour, is equal to 1. Okay, we need to find the probability that in the first 15 minutes we have first customer entered, when we have the first customer entered in the first hour. Okay, so we need to find this probability. Now this is conditional probability. Okay, and when we have conditional probability, okay, then we can use the binomial distribution. Remember that. Okay, we need to use the binomial distribution. So we can also use the other traditional technique, but we can also use the binomial distribution. I will do it both ways. Okay, so first using the binomial distribution. Okay, so binomial distribution has two parameters. Okay, n and p, where n is the number of trials and p is the probability of each trial. Okay, so here, okay, n is equal to 1. Okay, because we have only one event occurring. Okay, so the n is equal to 1. Okay, now the probability that is need to be found. Okay, the probability is actually u by t. Okay, u by t, where u is this time 0.25 and t is the total time. Okay, so the probability is equal to 0.25 divided by 1, which is 0.25%, or 25% chances, okay, that this event is occurring. Okay, so p is equal to 25% and n is equal to 1. Now using the binomial distribution, okay, so the probability that the customer entered in the first hour, the first 15 minutes, such that only one customer entered in the first hour, it is equal to NCR, okay, into u by t raised to power k into 1 minus u by t raised to power n minus k. Okay, u over here is 0.25. Okay, we can also say that x of u is equal to k, such that x of t is equal to n. Okay, so comparing this, u is equal to 0.25, k is equal to 1, t is equal to 1, and n is equal to 1. Okay, so putting the values, n is equal to k is equal to 1. So we see that one combination of this is NCK. Okay, so one combination of 1 multiply by, as n is equal to k is equal to 1, multiply by u by t. U is 0.25 and t is equal to 1 raised to power k, k is equal to 1, into 1 minus 0.25 divided by 1 raised to power n minus k. N minus k is 1 minus 1. Okay, so one combination of 1 will give us 1. Okay, 0.25 divided by 1 will give us 0.25, and 0.25 raised to power 1 is equal to 0.25. Okay, multiply by 1 minus 0.25 is 0.75. Okay, raised to power 1 minus 1 is 0, so anything raised to power 0 is equal to 1, so it will become 1 multiplied by 0.25 multiplied by 1, which is equal to 0.25 or 25% chances. Okay, so we have 25% chances that the first customer, okay, enters in the first 15 minutes, conditional to the statement that we have only one customer that entered in the first hour. Okay, so that is how you solve the problems based on the conditional probability using the binomial distribution. I will also use the other method, okay, the traditional method. Now using traditional method. Okay, when we find the probability, when we have conditions over here like x of 0.25 is equal to 1 such that x of 1 is equal to 1, okay, it will be equal to the probability, okay, that x of 0.25 is equal to 1 multiply by the probability, okay, that x of 0.75, 1 minus 0.25 is 0.75 is equal to 1 minus 1 is 0. Okay, that in the other 3 quarters there are no customers. In the first quarter, okay, 15 minutes we have one customer. In the other 3 quarters we have 0 customers. Divide by the probability that in the first hour we have one customer. Okay, so now using the formula that P of or probability of x of t is equal to n, it will be equal to e raised to power minus lambda t dot lambda t raised to power n divided by n factorial. So putting the values in this form for this and this. Okay, so we have the probability that x of 0.25 is equal to 1 such that x of 1 is equal to 1. It will be equal to e raised to power minus lambda t. Lambda is 6 per hour. Okay, so minus 6 into t over here is 0.25. Okay, and 6 into 0.25 raised to the power 1 divided by 1 factorial. Okay, multiplied by e raised to the power minus 6 into t over here is 0.75. 0.75 dot 6 into 0.75 raised to the power 0 divided by 0 factorial. Okay, divided by p of x1 is equal to 1. It will be equal to e raised to power minus 6 into 1 raised to the power 1 divided by 1 factorial. Now simplifying this, we get e raised to power minus 6 into 0.25. It will give us minus 1.5. Okay, and 1.5 multiplied by 1.5 raised to power 1 will be equal to 1, actually divided by 1, so 1 factorial will also give us 1 multiply by, now 6 multiplied by 0.75 will give us e raised to power minus 4.5 multiply by 4.5 raised to power 0, so it will become 1, and 0 factorial also 1. Okay, divided by e raised to power minus 6 raised to power 1 is 6, divided by 1 factorial will become 1. Okay, so now we get 1.5 e raised to power minus 1.5 multiplied by e raised to power minus 4.5. Okay, 4.5 raised to power 0 is equal to 1, so we don't write it over here. Okay, divided by 6 e raised to power minus 6. Okay, now 1.5 taking the e common, okay, because bases are same, so it will become minus 1.5 minus 4.5 divided by 6 e raised to power minus 6, okay. So 1.5 e raised to the power minus 1.5 minus 4.5, it will become minus 6, okay, 6 e raised to power minus 6, okay. So this will be cancelled each other out, so 1.5 divided by 6, so it will become 0.25 or 25% chances, okay, which is the exactly same results as we got over here, okay, using the binomial distribution. So we can use either of these methods, to find the probability which is conditioned on another event, okay. Thank you.